So in the previous class, we studied about how we can write the equation of motion for our system using Newtonian mechanics, using Lagrangian mechanics, and using Hamiltonian mechanics. So if I have a large number of particles in the system, so after writing down the equations of motion, we need to solve the equations of motion. And to solve the equations of motion, we have number of algorithms that we will discuss in our today class. And after writing down the equations of motion, we will calculate the position and velocity or momenta of the particles in the system. So when after calculating the position and moment of the particles, we will write our property, our thermodynamic property as a function of position and momenta. So when we have number of particles in our system, so they are always going to interact with each other, and so there will be a force between them, and the force is defined by F equal to negative gradient of the scalar function V. So V is a scalar potential function here, or we will call it as a interaction potential as written here. So we can have a different type of interaction potential like Lj potential, like Morse potential, depends upon what kind of system we are studying. And the interaction potential is always dependent upon the distance between the particles in the system. And after and when we know the interaction potential that we are going to use in our system, we can calculate the force that is going to exist between the particles in the system. And also according to Newton's second law, we have force equal to mass into acceleration. So from these two equations we can write like mass into acceleration equal to negative gradient of our scalar potential function. So to solve the equations of motion, here you can see that we have velocity Verlet algorithm, we have leapfrog algorithm, and we have Beeman's algorithm. But the most commonly used algorithm to solve the equations of motion is velocity Verlet algorithm, uh, that is used in molecular dynamics. It is the mostly used algorithm to solve the equations of motions. So we are going to discuss velocity Verlet algorithm in today's class. So before I discuss the velocity Verlet algorithm, I will first discuss Verlet algorithm. Suppose I have particle I in the system. So if x and v are the position and velocity of the particle at any time t in the system. So to find the position of the same particle at time t plus delta t. So delta t is a small increment in the time. So to find the position of particle at the time t plus delta t, I will use the Taylor series expansion. So what I will do here according to the Taylor series expansion, so xt plus delta t, that is the position of particle at time t plus delta t, equal to the position of particle at time t plus the velocity of particle at time t into delta t, which is the small increment in the time, plus 1 by 2 factorial the acceleration of the particle at time t into delta t square. So you can see here, if this is the position of the initial position of the particle at time t, so here this term is nothing but the derivative of the position. The first derivative of this position is velocity, and acceleration is the second derivative of position here. So it will be the position of the particle at time t plus delta t. And if I write the same equation but just change the sign here, so the position of particle at t minus delta t, so it will be the position of particle at time t minus the velocity of particle at time t into delta t plus 1 by 2 factorial acceleration of the particle and delta t square. Okay, so what I will do now, I will add both these equations written over here. So when I add these equations, what I will get is the position of particle at time t plus delta t. It will be equal to the 2 into position of particle at time t plus the acceleration of particle at time t into delta t square minus position of the particle at time t minus delta t. And if I subtract these both the equations, then what I will get is position of particle at time t plus delta t minus position of particle at time t minus delta t equal to 2 into velocity of particle at time t into delta t. And upon rearranging here, what I will get the velocity of the particle at any time t equal to position of particle at t plus delta t, position at t minus delta t divided by 2 into delta t. So you can see here that when as in Verlet, in case of Verlet algorithm, I don't have any specific equation for calculating the velocity here. And the second thing is that if I want to calculate the velocity, that vit, if I want to velocity at any time t, what I need is the position of particle at t plus delta t and the position of particle at t minus delta t. So to have the position of particle at t minus delta t is we have to go two step behind. Okay, first we need to calculate the position at t, and we also need to have the position at t minus delta t. And also you can see here in the same equation that to calculate the position at t plus delta t, we need to have the position at t minus delta t, for which we have to go two step behind. Okay, so this is the problem with the Barlet algorithm actually. So to minimize this problem, we have a much better approach to do this. So this is we have a velocity Verlet algorithm. Okay, this is velocity Verlet algorithm. So what is velocity Verlet algorithm is the first equation is same as in the Verlet algorithm to find the position of the particle at time t plus delta t. And we have another equation here is to find the position the velocity of the particle, because in molecular dynamics, as I talk about, or I talk about classical mechanics, we are always interested to calculate the position and velocity of the particle. Okay, we are not only interested in the position, but we are also interested to calculate the velocity of the particle. Okay, so that was the drawback in case of the Barret algorithm. So here we can calculate the velocity at time t plus delta t, and it will be equal to the velocity at time t plus delta t by 2, and this is force at time t and force at time t plus delta t. When it is divided by m, so it becomes nothing but the acceleration. Okay, so now I will discuss how we are going to use this equation to actually calculate the position and velocity of the particles in the system. So initially what we are going to do, the general procedure that I am going to discuss here is, first we will use the first equation. Okay, so if we have the initial position and initial velocity of the particle in the system, so I can update the position of the particle at time t plus delta t by using this equation. Okay, so after finding the position, I need to calculate the velocity. But before calculating the velocity, I need to calculate the force. Okay, I need to calculate the force, and this is the most difficult part uh, in case of this velocity Barret algorithm. to calculate the position and velocity of the particles. This is the most complex part. Okay, so to calculate the forces here, uh, we have to use the equation that we discussed in the starting of the lecture, that this force is dependent upon the interaction potential that is going to exist between the particles. So after calculating, if we know or if we calculate the force that is at time t, and if we calculate the force that is at time t plus delta t, so we can easily calculate our velocity at time t plus delta t. So to calculate the velocity at time t plus delta t, we need to have the force at time t and also the current force that is acting upon the particle in the system. So first I have calculated the position, second I have calculated the force with the help of interaction potential in the system, and after that I will easily calculate the velocity, and I am going to repeat again. So again I will find the position, like I will find the position. I have initially find the position for delta t. After that I will find the position for delta 2t, delta 3t, and so on. So in that way, what happen actually, that this will generate trajectories of position and velocity that are computed at t equal to 0, t equal to delta t, t equal to 2 into delta t, or 3 delta t, and so on. So we will have trajectories of position and velocity of all the particles in the system, and when we have the trajectories of all the particles in the system, the trajectories of position and velocity of all the particles in the system, so after that we can calculate our macroscopic properties, that by writing uh, the properties as the function of position and momenta of the particles in the system. Thank you.